So the unique features of the normal distribution, right, these universally applicable features are really powerful. And what's interesting is that there are a lot of different variables are normally distributed. Let's say height, weight, intelligence, academic achievement on tests. All these are normally distributed, but they are on different scales, right? Height would be in feet and inches or centimeters. The weight would be in pounds or in kilos, right? And even there, you see if it's in pounds, it's on a different scale than in kilos, although the weight is the same. So here, a similar example, let's say SAT scores, right, on a scale that has a mean of 500, and then we see one standard deviation below is 400, one standard deviation above is 600, so the difference here is 100 points, which means that one standard deviation is 100 points. Right? Now we could say the same or similar thing for the ACT score. 20 points are the average. Then we see 25 is one standard deviation above, 15 is one standard deviation below. So 20 to 25 is 5 points, so that one standard deviation is 5. Right? Now, if we want to make these two tests comparable with each other, right? Let's say you have 25 points on the ACT score and 600 points on the SAT, right? We would know, if we knew the standard deviations, we would know that you're about one standard deviation above the average. And what we just did now is we calculated a z-score, right? So z-scores is a metric in terms of standard deviations. And so a z-score of 0 means 0 standard deviations above or below the mean, so it's the mean. A z-score of 1 means 1 standard deviation above the mean, or a z-score of -1 would mean -1 standard deviation below the mean. So if you want to combine different scales or compare them with each other, you can transform the scale into z-scores. The formula to calculate z-scores is here. Z equals the raw score of the individual minus the mean of the group divided by the standard deviation. Another way to write this is x, which is the score for the individual, minus x bar, which is the mean, divided by s, the standard deviation. So let's say we have an individual with a reading score of 43, that's x, and we know that the average reading score is 38.57 m, and the standard deviation is 4.56. Right, we could plug this into our formula. X is 43 minus the average, right? So that would give us the distance of the person to the mean. Right? We see here that this is a positive number divided by the standard deviation, right? So then that would standardize this difference in points. By dividing it by the standard deviation, we standardize it. So it's 0.932, so almost 1 standard deviation above the mean. We do the same thing for math here. So 67 is the individual score. Pull it down, 67, and then 65 for the mean. So 67 minus 65, we see this person is 2 points above the mean. Now what does that mean in terms of standard deviation? 2 divided by the standard deviation of 6.97 tells us that it's 0.287 standard deviations above the mean. So about a third of a standard deviation above the mean. And now we can compare the relative standing in reading and math. And we can tell that this person does quite a bit better in reading overall than in math. Now we could convert these z-scores also into percentiles, right? We could see, okay, this is the z-score metric down here. Now a z-score of 0.287, if we pull that up here, it corresponds to the 61st percent rank, right? So 61% of the people have lower scores than this person, and 39% have higher scores. At the same time, a z-score of 0.932 corresponds to the 82nd percent rank, right? So only 18% of the people have higher scores, and about 82% have lower scores. So if you want to figure out what percentile rank corresponds to a z-score, that's always the same. Remember, it's the normal distribution is universal. So there's actually tables that are published that tell you exactly which z-score corresponds to which percentile. Or nowadays you could also find calculators online that would tell you exactly what percentile rank a z-score corresponds to. Now, what happens if you know the z-score, but you want to know the actual value on the original scale? So what we would do is we would modify our formula, just move the terms around so that the x, the original score, becomes our variable on the left, and we have all the known variables on the right. And now we can figure out that if we know the z-score, it will be 0.93 times the standard deviation plus the average would give us the actual score for the individual. So here we figured out that the score had to be 42.99, which we start out with 43, close enough. Same thing for math, it was 67.